Okay, so this video is about the displacement of a particle. We'll talk more in depth about how a particle is displaced over time. And this is the question we're going to begin with. So a particle it moves along a horizontal line so that its position at any time t greater than or equal to 0 is given by this function where s is measured in meters and t is in seconds. All right, because it's moving around along a horizontal line, at some point in time, this particle will have a negative velocity, meaning that it's going backwards and forwards. Like it's not really just going in one direction. It's going back sometimes, forward other times, because it's all got to be on straight lines. It's on some kind of a string or some road, and it can't veer sideways. It just goes back and forward. So keep that in mind as you start thinking about this displacement. But basically, this is it. This is the function. So I can think about this two ways. One way I consider is velocity, or I consider just the path of the particle, which is given by this equation. So I'm going to actually erase all this because we need Desmos and I'm going to need some algebra to explain it. So if you would, copy all this. And I'm giving the question here. So this is the question. What is the particle's total displacement on an interval t is in between 0 and 5? You might write this as an interval notation. You could see it in some book as from 0 to 5 for time. Or you can see it as an inequality. All right, so anyway, I'm about to erase the screen and the question. So do copy it, and we're going to talk about it again now. So one way to consider this function is we could consider its graph. So let's actually graph it on Desmos. So this is the graph of the function here on Desmos, from time being 0 to time being 5, and it meets around right there. So its displacement is how far it moved from 0 to 5. So apparently the graph at 0 is somewhere around here, at 0.8. Then it moves downward, and then it gets to the bottom, and it goes up, it gets to the top, and goes down again. So even though it might be moving downward, we consider that a positive movement. And even though it might be moving beneath the x-axis, we also consider that positive movement. So if you have any y values that are negative, we consider the absolute value of that displacement as a positive number, because if I went negative 5 feet, I still went 5 feet, just in the wrong direction. So keep that in mind. So anyway, so the best way of finding it is, I would consider just the original function. I'm going to talk about two ways. I'm going to talk about one with the original function and also with the derivative function. So let's consider it first with the original function. All right, so let's consider its original function. It has a place where it crosses right around there at 0.8. Bottom's there at negative 0.631. So talk about the distance there. The distance from here to the line, as far as the y direction, that y value there is 8. And then this piece right beneath here, that's negative 0.631 beneath. So even though it's negative, I consider my distance by travel, 8, plus the absolute value of negative 0.631, plus it comes back up after there. So here, it goes back up in positive direction, that same distance in y. So plus another 0.631, and then it goes up a while. It goes up to here. So considering I can find that max pretty easily here, I know that that displacement from here upwards is about 2.118. So I can add another 2.118. Keep in mind that's absolute value symbols. Those aren't ones here. That's absolute value symbols around this decimal. So I can add that. And then it goes down, the same distance, get back to the axis. So plus another 2.118. And then plus, then it dips a good ways from here to where it meets 5. It looks like it meets 5 right around there. It looks like it's about, a good estimate for it, it's about here. So at 512, negative 12, if I saw that really well. Basically at 5, negative 12, that's another coordinate. You can see that right there. So negative 12 is its depth. So I'm going to add absolute value of negative 12 to it. So if I add all those things up, this should be, one second. its total displacement is about 25.5 meters from 0 to 5. So that's its total displacement, about 25.5 meters. Now, we can find, like here, it's pretty easy with decimals. It gives you the coordinates there. If you had a graphing calculator, you could zoom in and you can find out where these coordinates are. Like you can estimate that coordinate, you can estimate that coordinate on the table, estimate this maximum. You can kind of go around and get a good picture where it crosses there. And you can get a good idea where it crosses down here as well by using estimation with those coordinates. 1 second. So anyway, so you could find it pretty easily using that information. Now, if you can't use a calculator, for some reason you're taking some tests where you can't use a calculator, you can't find these coordinates exactly. You don't have to use a calculator to find these coordinates. I thought it is, Cal, there's no reason why we couldn't find those coordinates. So right now, I'm going to take a moment to actually talk about where these coordinates must be. So right now, we know the total displacement has to be 25.5 meters on that interval, and that's the answer. I mean, we're going to find the answer different ways, though, to think about how we can actually show this more than one way. But that's the answer. It's going to be 25.5. So anyway, let's look at it a different way. All right, a different way to consider this is, if I want to find out where these places are, I have those max and mins, because that's pretty important. I want to find those max and mins. To find out where it is going to be at 0 or where it's going to be at 5 is pretty easy. I just plug in 0 or 5 into the original function. And that tells me output at 0, tells me output at 5. But to find the coordinates here, without a calculator, we would need to use calculus. So this would be a tangent, as a horizontal tangent. So we're looking for when the slope of the original function is 0. So we're looking for that slope. You're basically saying, when is the derivative equal to 0? So when is it equal to 0? And that would tell you these two places. That'll give you the x coordinate for those two places. You got to find a y coordinate, you have to take it and you have to plug it back in to the function. But you can find those coordinates using the derivative. So let's do that now. All right, so going back to this function we began with, and without the graph, let's think about it. It says, where are the places where this function has local max and local mins? And the reason why I'm asking that question is, our goal is to answer the question we began with, like, what is the total displacement of this function? So again, our ultimate question is, what's the total displacement on the interval from 0 to 5? Total displacement on that interval. That's our ultimate question. What is it? What is that total displacement? However, in order to do that, we have to know the local max and local min of that curve. That curve essentially looks like this. Something like this. So what we want to know is exactly where are these points. We estimated it, but we can find exactly where they are with derivatives. So let's do it. So considering that function, we want to know when you have horizontal tangents. So that's saying when the derivative is 0. Let's first find the derivative of that function. It should be negative 3t squared plus 14t subtract 14. And we want to know when it's 0. And that's probably not going to be factorable. It may be, not really sure, and I don't want to waste time trying to find out. So I'll go straight to quadratic formula. So it should be negative 14 plus or minus the square root of 196 subtract 4 times negative 3 times negative 14. All over 2a. All over 2 times negative 3. So this is basically negative 14 plus or minus square root of 28 over negative 6, which is, so these two values, this is about, time is about 1.45. I'm going to call it 1.45114. Let's be more accurate. and time is about 3.215. 3.215. So those are pretty much the times when this graph has a max and min. So if we want to find the total displacement, we could find those times algebraically, and we can find out exactly what those times are. This is exact. So if you need to be exact for whatever reason, and it is using rocket science, sometimes you need to be exact. So if you needed exact values, you can find the exact values. Or we can use approximations. And these are approximations after using the calculator to find those exact values. Let's compare these approximations for time to the approximations we looked at in the original function's graph. So let's do that now. All right, look at the original function's graph. There was a value here. We said the y value was negative 0.631 because we wanted displacement. But notice the time is 1.451. Our time, we said it was 1.451, essentially 1.4514, but essentially the same thing. Other time is 3.2152. Let's look at the graph. And here, it's 3.215 at the other value, which you said was 2.113. That's a pretty good estimation. That's 3.215, and ours is also 3.2152. So ours is a little bit more accurate, but for practical purposes, it's pretty good. It's a pretty good safe estimate. So we could focus on all the stuff with derivatives if we need to be exact, and we could find out the exact values there. Or we could just consider the original function, and inside is displacement by looking at the original function and deciding how far to go in the y direction each time. And keep in mind that the displacement that's negative, we'll call that the positive version of it. And that would be a really good way of finding those distances. So again, you're just finding the distance here. Oh, let's change that. The distance here, plus the distance here, plus the distance here, plus the distance there, plus the distance there, plus the distance where it meets 5. So you're adding up all those distances together. Whether it's negative or positive, you just make sure it's positive when you add them. And that gives you the displacement of that object, and it's always going to be true. I think that's a good way of answering it. Now, you may find other ways, you may find other ways to solve it, but that will work every time. That's why I stopped. That's all I have. Good luck.